Hello everyone, welcome to the next video of ECE 573 Advanced Embedded Logic Design Winter 22 labs. In the previous lab, we discussed about the implementation of this 8-point FFT along with the debugging and the execution time calculation as well as optimization. Now, in this video, we'll focus on implementation of the large size Fourier transform. So to understand the large size Fourier transform, we need to discuss some basics of the FFT theory. So let's start with the simple example. So we'll start with the two-point FFT. So we'll start with the two-point FFT. So in the two-point FFT, you can see that we have the output G, which is a vector of 2 element. Then we have the matrix W, which is the 2 cross 2 matrix, and the input G, which is again a vector. So this matrix, you can see that you have the W 0, 0, 2, then W 0, 1, 2, then W 1, 0, 2, W 1, 1, 2, and here you will have the G of 0 and G of 1. Okay, so in this case, your W is represented here as the e raised to minus j2 pi. So when I say W, say 1, 1 of 2, it is nothing but the, okay, so instead of 1, 1, I'll say that it is I and j, and instead of here, I'll use k, so it is nothing but the e raised to, okay, e raised to minus j. Okay, so instead of, okay, I'll just rewrite this one slightly better manner. Okay. So W of S, T and K is nothing but e raised to minus j 2 pi S T divided by K. Okay, this is how it is calculated. So here you can see that e raised to minus 0, so it will be 1. This is again 1, this is again 1, and then here it will be e raised to minus j2 pi, that is cos pi minus sine cos pi is there, and then the sine pi term is there, sine pi is 0, so you will get minus 1, and then here you will get g of 0, g of 1, and then here you will get the output G0 plus G1, and then you will get the G of 1, which is output G0 minus G1. So this is how you can find out the 2-point FFT. Let's move towards the 4-point FFT. So in the 4-point FFT, again, you will have the output G, which is the element vector consists of 4 elements. Then you will have the W, which is the 4 cross 4, and then you will have the G, which is again a vector of 4 elements. Now look at this W. Now this W, you can see that it is again the same way. It is the W 0, 0, 4, then W 0, 1, 4, W 0, 2, 4, and W 0, 3, 4. Okay, then here you have W 1, 0, 4, W 1, 1, 4, then W 1, 2, 4, W 1, 3, 4. Then you will have W 2, 0, 4, W 2, 1, 4, W 2, 2, 4, and W 2, 3, 4, and the last one will be W 3, 0, 4, W 3, 1, 4, W 3, 2, 4, and W 3, 3, 4. And then you can calculate the corresponding matrix values, which will be the complex values for in case of the 4-point FFT, and then you can calculate. For example, you can see that the first one here, you can see that, sorry. So here you can see that the first one will be 1, then 1, 1, 1. That is quite straightforward. Then here also you will have 1, 1, 1. Then W114. So you can see that you will have e raised to minus. So it will be e raised to minus j 2 pi, that is 1, 1, and divided by 4. So e raised to minus j 2 pi 4, that is nothing but the e raised to minus j pi by 2. And if you calculate the corresponding value, it will be cos pi by 2 minus j sin by 2. So you will get the corresponding minus j here. And then in the next one, you can do the same thing. Let's take the W124. You will get e raised to minus j 2 pi, then 2 divided by 4. So you will get e raised to minus j pi. So it will be cos pi, and that will be minus 1. Why I'm sharing this one? Because this weight factors for the large size FFT, you can calculate this on the fly, but it will take some computation and the time. But you can always store them into the header file, and you can pre-calculate it and store them in the header file. So that's why understanding how this matrix is calculated is very important. So now, if this is clear, then you can see that I can form the 4 equation for the G0, G1, G2, G3 by doing this matrix calculation. And then you can see that I can represent this e raised to minus j 2 pi 2 divided by 4, that is equal to e raised to minus j. Here you can see the e raised to minus j, that is 2 pi divided by, so it is equal to 2 e raised to minus j pi. Okay. And e raised to minus j pi, you can always write in terms of the corresponding e raised to in terms of the first term. So you can always write this in terms of the first term by having the negative sign. I leave it to you to calculate the corresponding equation calculations. Okay. Similarly, you can represent the this term in terms of this term with the minus sign. So what is the advantage here? That instead of having the instead of needing the 16 weights, because in the matrix is 4 by 4, instead of storing the 16 weights, you need to store only, here you can see that you need to store only 2 weights for the case of the 4-point FFT. If you remember, in case of the 8-point FFT, we had to store only 4 weights. In case of the previous code where we discussed about the 8-point FFT, we had to store only 4 weights. So if you look at our 4-point FFT example, you can see that we had to store only 4 weights in the code. Okay, so that's the advantage of identifying the relation between the different butterfly weights and then minimizing the storage. Okay, so this is how it is done. So you can see on the right hand side, your 8-point FFT is 4-point FFT. Okay, 4-point FFT can be broken down into the 2 stages. Okay, 2 stages. 2 raised to 2 is equal to 4. And the stage 1 is implemented into the 4 by 2-point FFT. Okay, so 4 by 2-point FFT, this one and this one, and then you have the final final second stage where you use the n-point FFT, n-point butterfly. So here you can see that for any n point FFT, any n point FFT, you can break down into the n by 2 point FFT, and this inside this n by 2 you will have the n by 4. Inside the n by 4 you will have n by 8, and if you go this at the end you will have the 2 point FFT, and this is how you can generalize for any size. So now while writing the application, how we are going to do this. So let's come back to our 8 point FFT example, which we have already done in the previous videos. So in the 8 point FFT example, so this is the 8 point FFT. So in this 8 point FFT, you can see that we have the 3 stages. Okay, we can break down into the 3 stages: stage 1, stage 2, stage 3. And in the before this stage, you need to take care of the bit reverse operation. Okay, that is one thing. And then for every stage, we can you can see that the we can break down into the multiple butterfly stage. For example, stage 1 consists of the 4 butterfly stage, 2 point butterfly. Then the stage 2 consists of the 2 4 point butterfly, and stage 3 consists of the 1 8 point butterfly stage. So this is how we can generalize the code. So before we go into the FFT part, bit reverse operation, in the previous case we did the hardwired one, but there is a logic we can use. For example, suppose we are doing the 8 point butterfly. So the corresponding binary representation of the index is like this. So if you want to find out the how to order the inputs, what we need to do, we need to just reverse the index. So 0 0 0 reverse is 0 0 0, 0 0 1 reverse is 1 0 0, so that is 4, and 0 1 0 is same, so 2, 0 1 1 it is 1 1 0 6. So you can see that we did the hardcore one, but we don't need to even do the hardcore one. We can always come up with the appropriate logic. So in the previous case, we can see that if we want to write the generalized code, then we might have to do a separate thing for each case, but this may not be a good option. So we need to come up with the logic which can do this bit reverse for any code. Okay, and the logic is that we just reverse the index. I'll show you how to do it in the C code. Now, how to do the second part? Second part is the part which is this one, FFT. So few observations which we can exploit during the code writing. We need to consider each stage separately. So you can see that we can break down our code into the number of stages. So we can have the for loop for each stage separately, and we can treat each stage separately, because we can't do the stage 2 before completing the stage 1. We can't do the stage 3 before completing this. So we can write a for loop for stage 1, stage 2, stage 3. Now, in each stage, you can see that the fixed number of weights are used for each butterfly. So if you see in case of the stage 1, we are using only one butterfly, which is the W08. Okay. In case of the stage 2, we are using the butterfly which is the W08 and W28. In the third one, we are using the butterfly W08, W18, W28, and W38. Okay, so you can see that we are using the fixed number of butterflies, number of weights in each stage. Okay, so here also you can see the fixed things are being used. So in the stage 1, we need only one weight. So in the stage 2, we need 2 weights. That we need to observe here. Now in each stage, in a given state, each weight is being used for FFT size into the number of distinct weight types. For example, in stage 1, there is only one weight, and this is being used for this output, 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 and this output. So FFT size is 8, and number of distinct weights in that stage is only 1, right? So that's why each weight is used for the 8 times. Now if you look into the second stage, in the second stage we have 2 weights, and you can see if you look at this weight, it is used for this output, then it is used for this output, and the same weight is also here. It is used for this output and it is used for this output. So this is used for the 4 times. 4 times is nothing but the FFT size, it is 8, and the number of distinct weights are 2, so that is 4 times. Okay, so this is the each weight is used for that number of times. Then how we can write our code? We can consider 3 for loops. We have one outer for loop for the number of stages. So we can consider one for loop which goes from stage 1, stage 2, stage 3. This is we need. Then we can consider the middle for loop, where we can have that for loop for the looking into the weights. Okay, for example, with this for the stage 1, we can have the for loop for this for the weights. For example, for the stage 1, there is only one iteration, so the for loop will have the only one iteration. In case of the stage 2, you will have 2 weights, so there will be 2 iterations. So the number of iteration is equal to the number of weights in a stage. In the stage 3, you will have the 4 iterations of the middle loop, because there are number of 4 weights are there. Okay, so this will be our middle for loop. And then after we have the inner for loop, which will be the number of times the weight is reused. So you can see that. So here, if you see in the first stage, this weight is reused 4 times. Okay, so we can have that loop, innermost loop, as 4 times. In this case, the weight is used for the 2 times, so we can have the innermost loop for the 2 times. And here it is used again. There are this is used only 1 time, so you can see that we can use it only. This iteration will be only 1 iteration. Okay, so the number of times weights is used, so that is the FFT size and the number of distinct weights of that one. So you can see that the corresponding stages are being formed. So this is how we can write the corresponding FFT code. Okay, so so that means in our code there will be 3 loops. One outer, we can have the outer loops for the number of stages. So for 8-point FFT, we'll have the outer loop which goes from the 3 times, stage 1, stage 2, stage 3. Then for every stage, we will have the middle loop, which will be for the number of bits. For example, for the stage 1, there will be an inner loop which will be executing, middle loop which will be executing only for 1 iteration, because there is only 1 bit. Then for the second stage, the inner loop will execute for the 2 times for 2 weights, and the third stage, the inner loop will be executing for the 4 times, because 4 loop. Then in the innermost loop, for loop, which will be, you can see that from the innermost loop we'll get the output. So at the innermost loop, we need to get the 8 outputs, okay, for every cases, right? So but you can see that for a given weight affects the 2 output, so we can, from 1 iteration of the loop, we can get the 2 output. So for example, if you are in the stage 1, I can just write simplify it. So if you are in the stage 1, okay, your outer loop will be for one iterations. Okay, that is the stage 1 outer loop. That is the first iteration. Then the middle loop will be only the 1 iteration will be there. Okay, and the innermost loop, number of iterations are FFT size, that is the 8. Number of distinct 1 is there. So you have the total 8 output. But now here you can see that the 1 weight affects the 2 output. So you can reduce the number of iteration instead of the FFT here by even 2. Okay, so you can have the number of weights at the stage into 2. So instead of 8, you can have the even 4 loops. Now if you go to the stage 2, in the stage 2, there is an outer loop of 1 iteration. Then your inner loop will have the 2 iterations. Okay, so this is the 1 iteration of the outer loop. In middle loop is of the 2 iteration because the number of weights are 2. And then the third loop, innermost loop, will have the FFT size, that is the 8 divided by number of distinct weights are 2 and into 2. So you will have the 2 iterations of the innermost loop, right? And each iteration will be giving you the 2 outputs. So you will get 4 outputs here from this one. 4 into 2, you will get the total 8 outputs. Okay, so from every stage you will get the 8 outputs, but the number of outputs in the middle and the inner loop will change depending upon the stage 3. So let's do it one more time. In the stage 3, the outer loop will have 1 iteration as mentioned. Then the middle loop will have 4 iteration, 1 for every loop, and the last loop, which is this one, which will have only 1 iteration for every weight. Okay, for every loop, inner loop, and each iteration will give you the 2 outputs. So 4 into 2, you will get the 8 outputs. Okay, so this is how the code, your code will work. Now we will discuss how this C code is implemented in the how this FFT is implemented in the C using the C code in the next video.